Well, welcome back to our course, Computer Organization and Architecture. We're getting into our next major section, and this chapter is going to be focusing on number systems, but just to give some context here. So we gave an introduction, and so this was a nice way to see the bigger picture when we're starting out to understand the concepts of computer and computer evolution. And then we got a chance to go a little bit deeper to thinking about the computer system, thinking about the function of computers and the interconnections. We went in a lot of chapters into memory, input and output. And then finally, in our last chapter, we spoke about operating systems and how they support the whole computational process that we're trying to put together. Now in this next part, we're going to be taking a little bit of a deep dive into thinking about how does a computer actually think. And so we need to be thinking of arithmetic approaches, how we think from a machine language, and thinking about logic, and we'll have digital logic. But for this first chapter, we're going to just introduce number systems. And so here is a summary of what we'll capture. We'll talk about the different types of systems, the decimal system. We'll talk about the octal system, the hexadecimal, and the binary system. And then we'll show how we can do the conversions between binary and decimals, and the hexadecimal notation in particular. So hopefully as a result of seeing this material, it'll be a little bit clearer, maybe not seem so difficult to do. And so now let's just try and give a couple examples and maybe think of the decimal system from a different point of view that you haven't thought about. In everyday life, we use a system based on decimal digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, to represent numbers and refer to the system as the decimal system. Consider what the number 83 means. It means 8 tenths plus 3. So it's 8 times 10 plus 3. The number 4728 means 4,702 tens plus 8. And so now we're seeing if we wanted to lay that out, we can see, or we can take each one of those at a time. So the decimal system is said to have a base or radix of 10. This means that each digit in the number is multiplied by 10 raised to the power corresponding to that digit's position. So for 83, it would be 8 times 10 to the 1 plus 3 times 10 to the 0. So it would be 8 tens plus 3. 4728 would be 4 times 10 to the 3 plus 7 times 10 to the 2, 2 times 10 to the 1, and 8 times 10 to the 0. So if you think from this point of view, I think it would help you get a better handle for how we go from one base to another. The same principle holds for decimal fractions, but negative powers of 10 are used. Thus, the decimal fraction of 0.256 stands for 2 tenths plus 5 100ths and 6 1,000ths. So therefore 0.256 is 2 times 10 to the minus 1 plus 5 times 10 to the minus 2 plus 6 times 10 to the minus 3. A number with both an integer and fraction part has digits raised to both positive and negative powers of 10. So if we wanted to consider 442.256, it would be 4 times 10 to the 2, 4 times 10 to the 1, 2 times 10 to the 0, plus 2 times 10 to the minus 1, plus 5 times 10 to the minus 2, and 6 times 10 to the minus 3. And any number, the leftmost digit is referred to as the most significant digit because it carries the highest value. The rightmost digit is called the least significant digit. In the preceding decimal number, the 4 on the left is the most significant digit, and the 6 on the right is the least significant digit. Table 10.1, which we're showing here, shows the relationship between each digit position and the value assigned to that position. Each position is weighted 10 times the value of the position to the right and 1/10 the value of the position to the left. Thus, Positions represent successive powers of 10. If we number the positions as indicated in table 10.1, then position I is weighted by the value 10 to the I. One other observation is worth making. Consider the number 509 and ask how many tens are in the number. Because there is a 0 in the 10th position, you might be tempted to say there are no tens. But there are in fact 50 tens. What the 0 in the 10th position means is that there are no tens left over that cannot be lumped into the hundreds or thousands and so on. Therefore, because each position holds only the leftover number that cannot be lumped into the higher position, each digit position needs to have a value of no greater than 9. 9 is the maximum value that a position can hold before it flips over into the next higher position. In a positional number system, each number is represented by a string of digits in which each digit position I has an associated weight R sub I, where R is a radix or base of the number base. The general form of such a number of a system with radix R is shown here, and I won't go ahead and read that, but you can think you're seeing how that would work. Where the value of any digit a sub I is an integer in the range from 0 less than or equal to a sub I is less than R. The dot between a sub 0 and a sub minus 1 is called the radix point. The decimal system then is a special case of a positional number system with radix 10 and the digit in the range of 0 through 9. As an example of another positional system, consider the system with base 7. This isn't really used that much, but the term what this represents is it's the octal system. Table 10.2 shows the weighting value for positions -1 through 4. In each position, the digit value range from 0 through 6. So those are the numbers. You can see how that would work. In the decimal system, 10 different digits are used to represent numbers with a base of 10. In the binary system, we have only 2 digits, 1 and 0. Thus, numbers in the binary system are represented to the base 2. To avoid confusion, we will sometimes put a subscript on the number to indicate its base. For example, 8310 and 472810 are numbers representing in decimal notation, or more briefly, decimal numbers. The digits 1 and 0 in binary notation have the same meaning as the decimal notation. So we have a case where 0 sub 2 is equal to 0 sub 10, and 1 sub 2 equals 1 sub 10. Those are some interesting cases that comes up. To represent larger numbers, as with decimal notation, each digit is a binary number, has a value depending on its position. And we're showing a couple examples here. I won't read these, but here we're seeing 10 base 2, 11 base 2, and 100 base 2, and we can see how that would fold out. And so if you just do this type of an expansion, just add the results, you can easily come up with what the number is. So again, the fractional values are represented with negative powers of the radix. And so we can also have binary fractions. And so we're showing that last example on the bottom here that you can see what that looks like. It is a simple matter to convert a number from binary notation to decimal notation. In fact, we showed several examples in the previous subsection. And what is required is to multiply each binary digit by the appropriate power of 2 and add the result. To convert from decimal to binary, the integer and fraction parts are handled separately. So here we have some more details for integers. For the integer part, recall that in binary notation, integer is represented by, so here we have that type of a system. Suppose it is required to convert a decimal integer n into binary form. If we divide n by 2 and the decimal system obtained a quotient n sub 1 and the remainder r sub 0, we may write n equals 2 times 10, 2 times n sub 1 plus r0, r sub 0 equals 1 or 0. Next, we divide the quotient n1 by 2, assume that the new quotient is n2, and the new remainder is r1. Then n1 equals 2 times n2 plus r1, r1 equals 0 or 1, and so we can continue that process as we go along to flush this out. So conceptually, this is definitely one way that you can be conceiving how you would go about doing this conversion. Because n is greater than n1, greater than n2, and so forth, continuing the sequence will eventually produce a quotient n sub m minus 1 equals 1, except for the decimal integer 0, 1, whose binary equivalents are 0 and 1, respectively. And a remainder r sub m minus 2, which is 0, 1. So we can be seeing how this equation would work. So, which is the binary form from n. Hence, we convert from base 10 to base 2 by repeating division by 2. The remainder and the final quotient 1 give us, in order of increasing significance, the binary digit of n. Figure 10.1 shows two examples. One of the things that will be helpful, and we'll be showing one a little bit later, is if you have like the factors of 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, etc., you'll start to get an easy sense of how to do these pretty much on the fly, but using some of the tricks the way that we've been looking at the notation so far. So figure 10.1 gives examples of converting from decimal notation to binary notation for integers. And so we can be, this is a formal way of doing this just by dividing by 2, and we just keep in mind what the remainders are. And so this is a formal way, the way you would be producing an algorithm if you wanted to do this, say, in Python or whatever your favorite language might be. For the fractional part, recall that the binary notation, a number with a value between 0 and 1, is represented by what we're showing here, and has a value shown here, so you can see that. And we can rewrite this into the way that they're putting it here in that expression. This expression suggests a technique for conversion. Suppose we want to convert the number f, where f is greater than 0 and less than 1, from decimal to binary notation. We know that f can be represented in the form as we're showing here. If we multiply f by 2, we obtain this following thing. And let's go ahead and continue on in the next slide here. From this equation, we see that the integer part of 2 times f, which must be either 0 or 1, because 0 is less than f is less than 1, is simply b sub minus 1. So we can say that 2 times f equals b sub 1, b sub minus 1 plus f1, where 0 is less than f1 is less than 1. And then we can be noticing this equation. I won't read that, but you can see that. To find b sub minus 2, we repeat the process. Therefore, the conversion algorithm involves repeating multiplication by 2 at each step. The fractional part of the number from the previous step is multiplied by 2. The digit to the left of the decimal point in the product will be a 0 or 1 and contributes to the binary representation, starting from the most significant digit. This fractional part of the product is used in the multiplicand. Okay, so figure 10.2 shows two examples, and so we can see that here. This process is not necessarily exact. That is, a decimal fraction with a finite number of digits may require a binary fraction with an infinite number of digits. just remember, like 1/3 is 0.333333. That's the kind of thing that we're talking about here. In such cases, the conversion algorithm is usually halted after a pre-specified number of steps, depending on the desired accuracy. So just like we can have it in base 10, we can have it in base 2, is what they're trying to have us think about here. Because of the inherent binary nature of digital computer components, all form of data within computers are represented by various binary codes. However, no matter how convenient the binary system is for computers, it is exceedingly cumbersome for human beings. Consequently, most computer professionals who must spend time working with the actual raw data in the computer prefer a more compact notation. So what notation should they use? One possibility is a decimal notation. This is certainly more compact than binary notation, but is awkward because of the tediousness of converting between base 2 and base 10. Instead, a notation known as hexadecimal has been adopted. Binary digits are grouped into a set of 4 bits called a nibble. So each possible combination of 4 binary digits is given a symbol. Because 16 symbols are used, the notation is called hexadecimal, and there are 16 symbols, and they are called the hexadecimal digits. So here are the ways of thinking about the decimal, binary, and hexadecimal. So we can see them one next to each other, and this goes all the way up to 256. And so you're probably starting to see a pattern here. And so seeing for one digit, these values from 0 to 15 is definitely something that's worthwhile keeping in your head, or having it quickly available so that you could be looking it up, because this is another way that you can be doing some quick conversions. Hexadecimal notation is not only used for representing integers, but also used as a concise notation for representing any sequence of binary digits, whether they represent text, numbers, or some other type of data. Reasons for using hexadecimal notation are as follows. It is more compact than binary notation. In most computers, binary data occupies some multiples of 4 bits, and hence some multiple of a single hexadecimal digit. It is extremely easy to convert between binary and hexadecimal notation. So those are all rationales why it is beneficial. So this is a relatively short chapter. We had a chance to see the decimal system. We got some insight into positional number systems as we start to break down the tenths, the hundredths digit, and then for fractions, the 10th digit, the 100th digit, and so forth. We got a chance to get introduced to the binary system, and then we looked at converting between the binary and decimals, both thinking in terms of integers and fractions, and then we got into hexadecimal notation. These are some things that we'll be looking at in a variety of different ways. You can be thinking, if you had to be looking at actual memory locations, you could be looking at those results in a hexadecimal format, a digital format, or it could be converted to decimal, or the normal decimal system. So there are going to be times when going from one to another is a quite useful tool. Okay, relatively short chapter, but thank you very much.